Okay, dokie. Today we're going to find the binomial series by solving a difference equation. Not a differential equation, but a difference equation. So let's take a look at what we'll be doing today. We want to find what the sum of this is right here. This series is right here, which is a geometric series actually. We'll have the absolute value of x be less than 1, then this series will converge. So let's try to find this this sum. What we'll do first is any sum can be written this way right here, where we have s of n plus 1 minus s of n equals a sub n plus 1. So let's see how we can use this to find any sum here. What we'll do is, there's the s sub n plus 1. I didn't do anything to that. Here's the s sub n minus equals, and what is a n plus 1? Well, this is the a n right here is x to the n. So if you stick in n plus 1 into the n, we'll get x to the n plus 1. And so a sub n plus 1 equals x to the n plus 1. So this is the difference equation for any series. This is the difference equation for this particular series right here. All right. We will rewrite this similarly to what we do with differential equations. We'll write this in terms of operators. If this is n plus 1 minus Sn, the operator e times Sn will give you the Sn plus 1. So this times this, e times Sn gives you the n plus 1, and negative 1 times Sn, of course, gives you this. So this is the same as this. And just like we do in differential equations, we'll solve the homogeneous, so we'll set this equal to 0, and we'll solve this difference equation very similarly to the way we solve a differential equation. So this is our homogeneous equation because it's set equal to 0 of this total difference equation. So we'll take the e minus 1 set equal to 0, solve for e, and you get e to the 1. And the way we write our homogeneous is a little bit different than a differential equation. The differential equation has a constant, and so does this difference solution. But what's different is when you solve for e, if you have e equals 7, it'll be 7 to the n. If it's e equals 1, though, it'll be 1 to the n. Of course, with e equals 1, you will get 1 to the n is 1, so 1 times a is a. So the homogeneous solution to this difference equation, not differential, but difference equation, actually is just a constant a, just an arbitrary constant. Okay, so we found this homogeneous. Of course, if you remember your differential equations, the next thing you'll have to do is find out the particular solution. So we'll look at our particular function. The particular function, of course, is sitting on the other side of the equal sign in a difference equation or a differential equation. But this is a difference equation. But the methods are somewhat similar. And just like we do with differential equations, once you have your particular function, you'll make a guess, your particular guess for the solution, a particular solution. And when we have this function, our particular guess will be just some constant times this function right here. So I used a already, so I'm just going to use b times this function and make this my guess for the particular solution. Review your differential equations if you are getting a little bit confused here. Okay. Well, once you have your particular guess solution, of course, we'll need to stick that particular solution into the difference equation. When you stick this into this term right here, n plus 1, that'll mean to stick n plus 1 into the n right here. So there's the n. If this is n plus 1, you'll get n plus 1 will give you n plus 2 right there. So you'll get b x to the n plus 2 if you stick that into there. And that's what I wrote right here. And if we stick this into here, it says just stick n into the solution. So if you stick n, you'll just get b to the x to the n plus 1. So you'll just get this back right here. So this term is this term with the particular guess solutions plugged into there. And this term is this term. Of course, there's the equal sign right there. And paper's covering it up, but x to the n plus 1, just like we do in differential equations, nothing happens to that. Okie dokie. From this, we will solve for Mr. B, which is usually what we do with even differential equations, but now we're solving for a difference equation. So B, if you do a little bit of algebra, will come out to be this. And if you can't do a little bit more algebra, you'll get B equals 1 over x minus 1. So our particular solution will be b times x to the n plus 1, which is what we said before. And so now we know who b is, so we'll take b and stick it right into here. And so 1 over x minus 1 times n plus 1 is equal to x to the n plus 1. I'm sorry, x to the n plus 1 is equal to x to the n plus 1 times 1 over x minus 1. So this is our particular solution. This is our homogeneous solution. And of course, we know from regular differential equations, which this is not, these are differential equations, but it works similarly, that our general solution is our homogeneous plus our particular solution. So that is the same for difference equations, just like it is for differential equations. So do you know your homogeneous solution? Yeah, that's A. So that person is A. Plus, do you know your particular solution? Yeah, that's x to the n plus 1 over x minus 1. So the particular solution is this person. So that's that, this is this, and that's that. And this is our general solution. And just like we do in differential equations, we'll need initial conditions. And we noticed that in our original series, if we stick in a 0 for our first term, a 0 in here, x to the 0, of course, is 1. So when n equals 0, if this was from n equals 0 to 0, the sum would just be equal to 1. So for n equals 0, we know the sum is equal to 1. Okay? So we'll take the 1 and plug it into the sum right there. That's what I did right there. A, I don't know, and x, I don't know. Right here, but I do know who n is. N is 0. So we'll get a 0 plus 1 is 1. So we'll get x to the 1. And here's the x minus 1 right here. So the only person we want to know in here is who is A. So we'll do a little bit of algebra and solve for Mr. A. And we'll get A equals this, which equals this if you do a little bit of algebra. So now you know, here is our general solution. We wanted to know who A was. And we use the initial conditions, kind of similarly to what we do in differential equations. And we found out that A was equal to this, so we can take this A and plug it into here and get, that's what I did right there. There it is. And that person right there is right here. And this is actually the solution. I'm going to do a couple of things. The first thing I'm going to do, this is for, of course, for x, absolute value of x is less than 1, which is what we said over here. So this is the solution if it doesn't go to infinity, if it goes to 75 or 122 or 5 billion. But what happens when n goes to infinity? Well, you'll get x to the infinity, and if the number is between -1 and 1, not equal to -1 or 1, like -1/2 or 0.3 in here, 0.3 to the infinity is 0. So if you want the n sum, this is the answer. If you want an infinite series, you'll get 1 over 1 minus x, because this will live, but 0.3 to the infinity is going to be 0. This term will go away right here. So the infinite sum is 1 over 1 minus x. Well, 1 over 1 minus x, of course, is the binomial series. So I guess this original series that we had here, after solving it, we got 1 minus 1 over x. So this is the same as the binomial series. And you'll notice it's also the sum of a geometric series right here. Okay, so I hope you enjoyed this lecture, and I look forward to any comments you have at the bottom. Thank you very much.